Bow your heads, please.
Dear God, thank you for this day and for bringing us all here to Miss Brady's class, and may you learn whatever she desires to teach us in your name. Amen.
Amen. Thank you, sir. Okay, now we have to remember what we learned in the last chapter because we're building on it, and chemistry is going to be like math in that way, that you're going to be building on concepts that you learn. And so kind of make sure you know something about what you've already done because you are going to be building on it. In the last chapter, we learned about ionic compounds. We learned that some substances actually give or receive electrons. What does an ionic compound start with? What are you going to look for? Metals. So an ionic compound will start with the metal, and what does it end with? A non-metal. Very good. A non-metal, which is over here, correct? Okay, and then the noble gases won't usually interact with anybody because they have a full valence, don't they? Even helium has a full valence of the 1s orbital is full. It has 2, correct? But everybody else there has an s orbital and a p orbital filled. And so I called that the Octet Rule. Everybody, unless the little bitty guys like hydrogen and stuff, everybody else is going for 8. They're going for a full valence because everybody wants to be like the noble gases. And the noble gases are noble because they don't get together with anybody else. So ionic compounds are made up of metals and nonmetals. Which one wants to give electrons?
Non-metal.
The metals want to give electrons, and the nonmetals want to take electrons, right? Because these guys have, you tell me, how many electrons do we have in this outer shell here? 1. They have 1 valence electron, therefore they want to give it away because then they can have a full valence underneath that. How many do the ones in this one want to give away? 2. So what is the charge they're going to develop? Plus 2, right, because if they give away 2 electrons, they're going to have plus 2. How about these guys? What charge are they going to develop? Positive 1. The metals will become cations because they will develop a positive charge, and we name them, God bless you, by naming the element and then putting the word ion afterwards. And then what about the nonmetals? The nonmetals are going to develop what charge? Negative. And once we get past 4, Tim brought that up last week, we know that they're going to develop negative charges, and I told you that you could take whatever group they were in and subtract 8 from it, and it would tell you their charge. So what charge is carbon going to develop in an ionic compound? No, carbon is a non-metal, and therefore it's going to develop a negative charge. It's in group 4, so you say 4 minus 8 is negative 4, so it's going to develop a negative 4 charge. Nitrogen is in group 5. What is the charge it's going to develop in an ionic compound? Negative 3. So it's going to be 5 minus 8 is negative 3. This is in group 6. So what is oxygen going to develop charge-wise? Negative 2. So that's 6 minus 8 is negative 2. How about these guys down here? They're called the halogens, which are in the group 7. What are they going to develop? Negative 1 charges, right? And what remember when we name these anions, these negative ions, we are going to take the name and put an "ide" ending on it. So chlorine is going to become chloride. Bromine is going to become bromide. And then when you name an ionic compound, you just name the first element, and then you name the anion. So you name the cation, then you name the anion with the "ide" ending. Do you have to designate any numbers when you're doing an ionic compound? No. The numbers are actually in the chemical formula, aren't they? And we saw last week that the chemical formula, like magnesium phosphide, we would look at the charge. This has a plus 2 charge. And then we would look at phosphide, which is down here in group 5, so it would get a negative 3 charge. I don't know if you can read my writing. It's pretty bad. That's a plus sign, believe it or not. And then we learned that you would flip-flop those, but what we're actually doing is balancing out the charges so the overall molecule has a 0 charge. But the easiest way to do that is to flip-flop them. So this one would get the 3, this one would get the 2. We remove the charges, and that would be magnesium phosphide. And you don't have to say anything more about it because anybody that can read the chart and knows how the ionic compounds work can figure out the charges and therefore figure out the subscripts that would have to be put in there. And you were just tested on that. Did everybody do okay on those? Okay. Tim, you had a question?
Do semi-metals change the
Metalloids.
what do they form molecules at all?
Okay, do metalloids change? Are they actually ionic compounds? Is that what you're kind of asking?
Yeah, because it's sort of metals.
It depends, because they can act like metals and they can act like non-metals, so it kind of depends on who they're together with. The ones we looked at last week, the copper 1 chloride and the copper 2 chloride, I would say those were ionic compounds, okay, because they were actually giving, and let me say this right up front now, because this is the definition that got me through college, because everything I made as simple as possible so it was easy to memorize. And ionic compounds transfer electrons. So remember that always. They transfer electrons. Now from there, you should know that if it's transferring an electron, then they're going to end up with charges, aren't they? And the electrical attraction is going to hold them together. Whereas covalent compounds, and you already read this, so I'm just going to say this real quickly. You already read that covalent compounds have covalent bonds in them, and that's why they're called covalent compounds. But covalent, they share electrons. So this is talking about what's happening to the electrons in both cases, okay? But ionic compounds transfer electrons and covalent compounds share electrons. Now, because they share electrons, are they actually going to end up with a real charge? No, because they share electrons. You already read, and we're going to go over this today, that polar covalent compounds, because they share unevenly, they can have a slight charge build up over the molecule, but they are not charged particles like ionic compounds are actually charged particles. They're made up of ions, okay? And like you were asking, the metalloids, don't worry, he's not going to try to fool you with them, okay? The metalloids, they can kind of do either way, so, but he won't try to fool you with it. I'll say that for him. And I'll always warn you if I find something on a test that I think you weren't prepared for. I make notes in my book to warn you. So, okay, so I would remember this because, like I said, that got me through college chemistry as far as a lot of problems. If you remember that the one is transfers electron and the other ones share electrons. Now, we also learned in the last chapter about Lewis structures. And, we learned some things about metals and nonmetals, which you were already tested on. The metals will conduct electricity. They have luster. They're bendable. The nonmetals don't conduct electricity. They lack luster, and they are brittle in general. And these guys are somewhere in between and very confused. So we won't go there right now. So in this chapter, we're learning about covalent compounds. Covalent compounds usually are made up of more than one nonmetal. And so they're not going to give their electrons because the metals are the ones that give them. And the first example he gives you is chlorine. I won't write it because it's right there in your book on page 127. But the chlorine, notice it's in group 7. And so basically the first 4 of group 7 would act like the chlorine, where they both want one electron, but neither of them is going to give it up. And therefore they will share. And you see that at the bottom of the page. And if they share that one electron, then they both think they have 8. and these two will share evenly because they're the same, made up of 2 of the same atom. So on page 128, he defines for us a covalent compound, a covalent bond is one where the electrons are being shared. And then when you have a molecule that's made up of 2 of the same atoms, it is called a homonuclear diatomic molecule. And he just defines it there as a molecule that consists of 2 atoms of the same element. So we are supposed to memorize there are 7 of those. And how I remember them is HNO. So you could just remember where they are on the chart, but I remember them HNO in the first 4 of group 7. Okay? Group 7's here, 1, 2, 3, 4. Not exactly sure why astenine doesn't work that way. But he wants us to know that it's HNO, which spells no, doesn't it? HNO, first 4 of group 7. And there are 7 of them. 1, 2, 3, 4, 5, 6, 7. Okay? HNO, first 4 of group 7. All right? So I'm just going to say HNO group 7, but you guys have to remember that it's only the first 4 of group 7. Okay? Okay, and this is going to become very important when we are building our own chemical reactions and stuff, and he says you're going to react oxygen. You have to know that elemental oxygen is always O2. Now, what do I mean by elemental oxygen? Those that I just told you, H, N, O, and the first four of group 7, in their elemental state, in creation, the way God made it, they exist as homonuclear diatomics. They do not exist as oxygen or hydrogen or nitrogen. Oxygen that we breathe is O2. That's how it exists. The nitrogen in the air is N2. Okay? So those things actually in their elemental form exist as homonuclear diatomics. That's very, very important. Everything else in its elemental form, you would just write Ba for barium. You wouldn't put it Ba2. But when you're dealing with these and you're writing them by themselves in their elemental form, you would write it as O2 or H2. Now, let me explain. If you had a reaction that it said hydrogen and oxygen were reacted together to produce water, okay, you would have to know to go back in this equation and go, okay, this is HNO group 7, HNO group 7, okay, and you would go back in and put the 2's in. Now, that is not a balanced chemical equation, and we'll learn that later. But the point is you would have to know to go do that. But you're not going to go over here and put a 2 in here because that's already in a molecule. You only add the 2's in their elemental form. That seems to confuse some students, so that's why I'm trying to show you this very clearly. It's only when these 7 are by themselves that they will be homonuclear diatomics and you will put the little 2 in. Once they are in a molecule with something else, they don't have to have the little 2 anymore. Okay? Want to be very clear on that because I know that confuses people. I've been teaching this long enough. I know that confuses people. And we'll come back to that, but I just wanted to show you because I know you guys are very familiar with H2O. We all know that. Little kids in the jungle know H2O, right? No, I'm kidding. Okay. All right, so he shows you there that the homonuclear diatomics, where they are on the chart, because that's an easy way to figure them out. It's the bottom of page 128. So it says, comprehension check. Number 1, we're at the bottom of the page. Draw the Lewis structure for bromine as it actually exists. Use a line to indicate the bond. So, in other words, bromine, because it is one of these 7, HNO group 7, the first 4, bromine is going to exist as that, isn't it? And so, yes, Jonah?
It would be the same as chlorine.
Exactly right. So we're going to write it. It's in group 7. So we're going to go 1, 2, 3, 4, 5, 6, 7. And then I'm going to put the other bromine here. And we are allowed to move these dots around now that we're trying to get them together. So I'm going to go 1, 2, 3, 4, 5, 6, 7. And this way I can make them share these two, correct? And so the way we're going to write that is with a line. That line designates a shared pair of electrons, okay? And so that means, and then when you do these Lewis structures with molecules, you should always go back and count them and make sure everybody's got 4 around them, except for hydrogen. Hydrogen only wants 1 pair, okay? But you go 1, 2, 3, 4, this guy's happy. 1, 2, 3, 4, this guy's happy. And that's important because when you start building these molecules, if you end up going back and counting them and somebody has 3 pairs around them, you're not done. If somebody has 5 pairs around them, you're not done. Okay? So you want them to end up having the right number. It's kind of like after you're doing a math problem, you want to check and make sure that you get the same numbers twice. Okay? Tim's asking if everybody under hydrogen acts like hydrogen. No, sir. This one only wants 2 because it's so small. It only has 1 electron, and therefore either it's going to ditch that 1 electron and become an H+, or it's going to grab 1 and become an H-. Everybody else here is going to be an H+. And hydrogen is usually an H+, and that's why it's put on the chart like that. Okay? Good question.
Yeah, what about hydrogen?
Good. Hydrogen is a nonmetal. And remember, hydrogen is a nonmetal. The only reason hydrogen is drawn on your chart all the way to the left is because it tends to want to give away 1 electron if it's going to, if it's going to become an ion, it will give away 1 electron, therefore it's drawn in the chart with the other ones that want to give away 1 electron. But when it's sharing in a covalent compound, because it is a nonmetal, and you have to remember that it is a nonmetal even though it's over there. See, you notice it's blue on your chart? It's a nonmetal. All right, now, over on page 129, we're going to do Lewis structures on covalent compounds. And remember, the covalent compounds are made up of non-metals, so nobody's giving electrons away. Everybody's just sharing. We're just sharing. Woo! Okay, and so he shows you there how carbon goes together with 4 hydrogens, and he shows you on the page how that's an example of that with the hydrogen, isn't it? First, you take the carbon, it's in group 4, so it's going to have 1, 2, 3, 4 valence electrons. You have 4 hydrogens.
Show us methane.
What did I say?
What?
Did I say something wrong?
No, I just said he's showing us methane.
Right. He's showing us methane, exactly. Okay, now, what you're going to do is play connect the dots, basically. Okay. And this is where pennies come in. If you get in a jam with these, get your pennies out. Start moving your pennies around. No, I have had students that really had trouble with this, and when they got their pennies out, it was easy. And I said, wow, that is brilliant. Get out some pennies, because with each one, you can only work with exactly the amount of valence electrons you have. But the point is, because trust me, some of these are going to get very difficult. Like ozone still confuses me, okay, which is O3. So the point is, you get pennies out and do it, it makes it a lot easier. So if you get in a jam, get your pennies out. Anyway, you're going to rewrite this as this. Now, here we have the hydrogen. Hydrogen only wants 2 around it. Each of those hydrogens has the 2 around it, doesn't it? But the carbon has 4, 1, 2, 3, 4, and that's what carbon wants. So carbon's happy. This is an H. I know it's really ugly. I'm sorry. Okay, and so that would be the Lewis structure. I'm sorry?
That looks like a U at the top one.
Yeah, I know. It's really ugly. I'm sorry. Okay, that would be the Lewis structure for carbon excuse me. It is methane. You're right. It's methane. I know what it is. It's early still. Okay, and on page 129 it says hydrogen's ideal electron configuration is 2 valence electrons, not 8. So we have been discussing that in some detail. Okay, so we're learning how to do Lewis structures for covalent compounds. And at the bottom of page 129 he says covalent compounds are a compound whose elements are held together by covalent bonds. Okay, so we call them covalent compounds because they have covalent bonds, which means they actually have shared pairs of electrons. That's what I want you to drill into your head, okay? And so and way back on page 52, a long time ago, we had, there were a few things that he referred back to here. On page 128, he referred back to a compound must be composed of 2 or more elements. That was back on page 44. That when we memorized what a compound was, you don't have to look, but it's on page 44 if you want to. But the point is, he defined a compound as something that has 2 or more elements, which means homonuclear diatomics are not compounds, are they? No, because they don't have 2 or more elements. They have 2 of the same element. And therefore, it's an element, not a compound by definition. Okay, and I went back and wrote down where these pages were found because I wanted to know myself, all right? And then the molecule was defined on page 52 for us, and a molecule is defined as a combination of 2 or more atoms. So now, is this in its elemental form, hydrogen or nitrogen or oxygen? Are they molecules? Yes, because they're 2 or more atoms combined together, okay? But they're not compounds because compounds have more than 1 element in them. See the difference? Okay, because he pointed that out, so I wanted to point it out also. All right, so then we go on to page 130. Covalent compounds do not contain metals. I kind of said that already. Here it is, Tim. But they can contain metalloids, right there. Okay, and on page 130, right under the pink box, the first sentence says, they can contain metalloids, but not metals. All right? Okay. And so he says you can tell whether it's ionic or covalent by looking for the presence of metals. I have all this starred because you really need to know what's in this little section right under the pink box. And if there's at least 1 metal, 1 non-metal, it's ionic. If there are only non-metals and metalloids, it's covalent. That you need to memorize. It should have been in a pink box. Okay? So just in your mind, put it in a pink box. All right. And then we're going to treat these as jigsaw puzzles as we build these guys. So let's look on the example problem because we need all the help on these we can get. And the first one, it says, do the Lewis structure for NCl3. So first I'm going to write it over here, NCl3. Now, he actually gives us, he doesn't set out rules until he's summing things up. But let's go over to page 133 and see how he sums things up, okay? So we're supposed to be trying to learn how to draw Lewis structures. And I want to give you, he gave rules on page 133, and he didn't set them apart in a bulleted form. But on page 133, the second paragraph on that page, second line down, you with me? It says, to build the Lewis structures for such covalent compounds, it is best to start with the atom that has the most unpaired electrons, put it in the center, try to attach all the other atoms to it. You probably just blasted past this and really didn't think too much about it. Let me give it to you in a written form, and that might help, okay? So when you're doing a Lewis structure of a compound, this is not my list, it's somebody else's list, but I thought it was pretty good. You should count the total number of valence electrons that you have to work with, because you want to make sure that you don't end up with any more or any less than what you started with. That's important. Conservation of matter. It's neither created nor destroyed. It can only change form, right? So important. Okay, number 2, just what he just said there. You're going to put the atom with the most unpaired electrons in the center. So place atom. I would suggest you guys write this down if you're not already. Place atom with most unpaired electrons in center. And if there's more than one of them that have the same number of unpaired electrons, put them both in the center and hook them together, and then put the other ones around it. Okay? Number 3, trust me when I tell you, these are simple that you're learning now. They're not always going to be. These rules will help you. Ozone is one that still freaks me out to do it. But if you follow these rules, it makes it easier. Number 3, you're going to arrange the other atoms around the central one and then start bonding. So arrange other atoms around the central one. And then start bonding. Sounds like we're going to youth group. Or fishing, whatever. Okay, so you start bonding them together. Now remember, the top anyone can have is 4 pairs of electrons, right? You know that? So you want to make sure that they have, each has, when you get done, 4 pairs of electrons, because what would that represent? 4 pairs of electrons, what would that represent? An octet, right? They've hit their 8, unless it's hydrogen. And so, unless hydrogen, which hydrogen you only want to have 2 electrons around it, right? 2 electrons. So it should only have 1 pair going to it. Now this is important because on a test or something, you can work really, really hard, get it all done, and if you go back and count them, you'll see you only have 3 pairs of electrons around one guy and 4 around the other guy. That doesn't work. You got to change something. So you've got to make sure that you have 4 pairs of electrons around everybody except hydrogen, who only needs 1 pair. Okay? And remember, these lines represent pairs. So let's use those steps. What do you say? So let's go back on page 130, and let's look at this. We have nitrogen, which is group 5, and so how many valence electrons is it going to have? 5. Chlorine is in group 7. How many valence electrons is it going to have? 7. So who are we going to put in the middle? Nitrogen, because nitrogen has the most unpaired electrons. So we're going to put it in the middle, and we're going to go 1, 2, 3, 4, 5. Now, I know I'm going to want to get chlorine attached to these unpaired electrons, aren't I? So I'm just going to put my chlorines here. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. I can move them around now, can't I? Okay. And then I'm going to make pairs of these electrons that aren't paired up, because I want you to notice I have a pair here, pair here, pair here. Here, 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 and here. I want you to see them. Okay? Now, we have to check and make sure everybody has 4 around them. Hydrogen would only get 2, but we're not dealing with hydrogen here, are we? So, 1, 2, 3, 4. Woohoo! 1, 2, 3, 4. Woohoo! 1, 2, 3, 4. Yay! 1, 2, 3, 4. Everybody's happy, right? So we get a Snoopy dance on that one? Yes, yes, rah, rah. Okay. So when we wrote this over again, he shows you in the book, you would actually just write it without these ridiculous little circles, but you would write it as N with the line, 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 Cl, and then you would put these pairs of electrons out there. If he's asking you for a Lewis structure, you have to show these electrons. Okay? Okay, let's do another one, and let's try the rules again. So the next one, he has water, H2O. Now, you tell me. I'll show you. First off, how many valence electrons does hydrogen have? 1. And I've got 2 of these. How many valence electrons does oxygen have?
6.
6. So who am I going to put in the middle? Oxygen has the most unpaired electrons, right? So it's going to be 1, 2, 3, 4, 5, 6. Correct? So I'm going to make a pair here. I'm going to make a pair here. And I would rewrite this like that. Now, he tells you in the book, and if you look on page 131, below the end of the example problem, you see all the different ways you could have written water in a Lewis structure that would have still been correct, okay? Only right now. Am I on the wrong page?
No.
131? Only on right now, because once you learn molecular geometry, you will not draw it any of those other ways. You'll draw it this way. Because water exists as a bent molecule, and you're going to know that soon. And you're going to know the bond angle on this and the whole bit. Okay? But for right now, you could have written it any of those other ways, and the Lewis structure would have counted as correct, because what you'd have had was 1 bond for each of the hydrogens, 1, 2, 3, 4. You've got 4 pairs around the oxygen, and you have 2 pairs that are unshared, right? See, and later you're going to learn why those pairs of unshared electrons actually bend the molecule, and that's why it's a bent molecule. Steele, did you have your hand up, sweetheart?
Yes, ma'am.
Yes, sir.
So
Can I erase this, or is it pertaining to this?
it's not really.
Oh, okay. Go ahead,
I
sweetheart.
was gonna ask. So it said covalent compounds do not contain metals. So that means only so metals aren't you don't have to combine metals.
Metals make ionic compounds.
Okay.
Metals share, transfer electrons. Non-metals share. Now, when a metal gets together with a non-metal, everybody transfers. Because the covalent is so happy to take it, the non-metal, I got it. The non-metal is not the covalent, shame on me. The non-metal is so happy to take it from the metal that it will take it, and you'll make an ionic compound. But when there's not a metal around, none of those non-metals are willing to give it up. So all they're going to do is share. Okay?
That's cool.
You can look at it that way. Yeah. Okay, good. That's good that you did notice that. Now look at number 2, comprehension check number 2. We're supposed to draw these Lewis structures. You already know how many valence electrons does hydrogen have? Guys, 1. And what about chlorine? How many valence electrons does it have? 7. So we're going to go 1, 2, 3, 4, 5, 6, 7. So we're going to connect the dots, and we're going to rewrite this way. And that would be the Lewis structure. Okay? The next one is CH3Br. Now let's play with that one. We got C. How many does carbon have as far as unpaired electrons? 1, 2, 3, 4. I have a feeling he's going to be in the middle, because nobody else has, unless they're in group 4, they don't have 4 unpaired electrons. So he wins. Woohoo! He gets the prize, being in the middle. We know that hydrogen has 1 each, so I'm just going to strategically put my hydrogens around here. And how many is bromine going to have?
7.
7. So I'm going to put him over here. 1, 2, 3, 4, 5, 6, 7. And then I'm going to play connect the dots. There we go. And so then I'm going to rewrite this. I know when you do these and your mom hears you, she's going to wonder what you're in there doing. Anyway, all the hydrogens, I'm serious, all the hydrogens have the one pair, so they're happy. The carbon has 1, 2, 3, 4, so he's happy. Bromine has 1, 2, 3, 4, it's happy. Notice once again, in this molecule, the way it's written there, CH3Br, I can do this, Br, I can write, really. Br, I want you to notice bromine is not a 2. It's only in its elemental form that it's got to have the 2. So I want you to just kind of drill that in your mind. Okay? Okay, we good so far? Okay, let's do the next one. And like I said, I think rules help. They help me. So now we have potassium oxide. Well, we'll say K2O, okay? I don't want to be wrong here. Well, it really is potassium oxide. And so
Isn't that ionic?
it is an ionic compound. We already determined that it is a ionic because it's got a non-metal in it. So we know potassium is going to give up the electron, don't we? Right? It's in group 1. It's going to develop a +1 charge, and there's 2 of them, so we're going to go like this. And then oxygen is actually going to grab those, so it will end up being a -2, and so it's going to end up like this, isn't it? So what do we see here? We see there that the metals will end up with no electrons around them, right? Because they want to give them away. And the non-metal will end up with an octet around them. And then we have the charges. So that's actually the Lewis structure for that compound. Did we? Yes, we did do Lewis structures for ionic compounds in the last chapter, didn't we? We didn't do the actual compounds a bunch, though, right? We just did the Lewis structures on the ions themselves. Okay. And then the last one is SF2. You guys tell me, if sulfur is in group 6 and F is in group 7, who's going to be in the middle? Here, I'll write it here so you can see it. Okay?
Yeah.
Which one's going to be in the middle? Sulfur is. It's got the most unpaired ones, doesn't it? Because chlorine only has 1 unpaired electron. So if we go like this, and we go like this, right? Then we would rewrite it.
The phrase, fluorine.
Oh, got it all wrong. Got somebody in group 7, just got the wrong guy, don't I? Thank you very much. So I'm going to put F here. F here. F here. They are different. They are different. Remember, everybody within the group, if they're all metals, they're all going to have similar properties. But you already studied this now because you've read what you were supposed to. They have different electronegativities and different sizes, and so that's going to make them act differently, right?
Do you add the IDE to fluorine, and does that become fluoride?
No, very good question. We only do, oh boy, Steele, that is just such a lead-in. Thank you. We only do the "ide" ending when it's an ionic compound. Very important. In the other books, they used to put all this in the same chapter, and people would inevitably miss them on tests left and right because they just taught all this in the same chapter. And he separated it, and I'm glad. In the last chapter, you learned that ionic compounds, you end with the "ide" ending with the anion ticking on the "ide" ending. Here, we don't have an anion, do we? And beyond that, in covalent compounds, they can get together in more than one way because they're sharing, they're not transferring. So in other words, the example he gave in the book, which is a real simple one because we're all familiar with it, is carbon monoxide and carbon dioxide. Carbon monoxide, carbon 1, 2, 3, 4, and then your oxygen 1, 2, 3, 4, 5, 6. Okay? Now this is a harder Lewis structure. But what you're going to end up doing is going like this, and then this pair. So it's going to be like this. Let's see, 1, 2. And we're going to have to move one of these over here, aren't we? 3. Okay, that's tougher. That's why I said you want to get together with the pennies. Okay, because what I saw was, let me just show you this step by step. What I saw was that if I went like this, these two would come together over here, right? I went like this, I went like this, I went like this. But when you count, 1, 2, 3, he's not happy. 1, 2, 3, 4, he's happy, but he's not happy. So how do I make both of them have 4? I'm going to grab this pair and move it between them. And that's what I did. Do you see it? All I did was grab this pair and move it between them. When I did that, 1, 2, 3, 4, 1, 2, 3, 4. Both of them have 4. Both of them are happy. Now that is you're not learning that yet. You will, but you're not yet. But I wanted to show you carbon monoxide can exist, and carbon dioxide can also exist. This actually exists like this. And I just know because I've done it so many times, I have it memorized. Okay? Now this is shared pairs of electrons, so that other one I just showed you had a triple bond, and these guys have double bonds. And the double bond is stronger than a single bond, and a triple bond is stronger than a double bond. Okay? Okay, but your question, and this is where I'm going up to, Steele, I'm not trying to be obtuse. You have to learn this stuff anyway. But look, what we have, when we look at covalent compounds, with ionic compounds, we said there's only one way there for them to get together, right? Yes, I know, it's okay, I've got more. There's only one way for them to get together, right? So we only have to name the first one and the last one, and then we can figure it out from their charges. You can't do that with covalent compounds, can you? Because if I just said carbon oxide, first off, the I would say that this was an ion, and it's not, okay? It's a covalent compound, so I can't do that. Second off, we wouldn't know which one we were talking about. So to do that, we have to have a different naming system, don't we? And the naming system on that, we kind of are leaping ahead, but go to page 135, please.
Oh, I see.
Yes, and so, but I'm answering your question, Steele. So to name covalent compounds, you're going to say, this would be carbon monoxide. Now, why do we name it that? Well, you don't have to put the mono for the first guy when he's individual. But when the second guy is just one, you're going to put mono there. And you still are ending it with ide. Okay, carbon monoxide. This one would be carbon, but there's 2 oxygens, so it's going to be dioxide. What if we had 2 carbons here? And I'm just trying to show you so that you're learning how to name them. If I'd have had this, I'd have put dicarbon dioxide. Okay, so if the first one's alone, it's the only time you pull off the prefix that determines how many of them are there. But look, you're supposed to memorize those prefixes on page 135. If there's one of them, you put mono in front of it. 2, di. 3, tri. 4, tetra. 5, penta, like the pentagon. 6, hexa. Yes, sir, Jonah.
On Untitled Chapter 3, he has us use the movie structures for CO and CO2.
Oh, well, let's do it.